So we're going to start off this session with Meirav Zehavi, who will talk to us about some graph structures in which we can find temporal disjoint paths and walks.
Thank you. And thank you for inviting me, and thank you everyone for listening. And please feel free to stop me at any point during the time and ask questions. Okay, so I'm going to talk about temporally disjoint paths and walks from the perspective of parameterized complexity. And this is a joint work with Pascal and Hendrik. Both of them are present in the workshop, in the room or online. And this is based on a joint work that was published in this ICALP. So just that will be on the same page. I have just 2-3 minutes on parameterized complexity. I know that now this is well studied for temporal graph, but still just the basics. So in parameterized complexity, we deal with parameterized problems. So this just means that each instance of our problem is associated with a parameter k. And the parameter can be essentially anything. For example, if we deal with the graph problems, say a vertex cover, then the parameter can be the maximum degree of the graph, the size of the solution we are looking for, the size of the vertex cover, how close is the graph to being a tree, and more. And the main notion is, yes. Okay, I thought there was a question. So the main notion here is that of fixed parameter tractability, FPT. And we say that a problem, parameterized problem, is FPT if it is solvable by an algorithm that has this running time, some function f that depends only on k. I hope that you can see my mouse. If not, then please let me know. So this is some function that depends only on k, the parameter, times the polynomial in the input size. So n is the input size. And these running times are interesting because when the parameter k is substantially smaller than the input size, they can be very efficient. Of course, depending on what the function f here is, can be 2 to the k and it can be 2 to the 2 to the k. Okay, but still, when the parameter k is small, these running times can be very efficient. Particularly, they can be better than doing some brute force. So if I'm looking for a solution of size k, I can brute force to find it in n choose k times some polynomial. And intuitively, why these running times can be better is because when we deal with an NP-hard problem, then we have some combinatorial explosion in the running time. And when we have a running time of this form, then the combinatorial explosion is confined just to the parameter k, just to our parameter, rather than let it depend on the entire input size. Okay, but not all problems are FPT, of course, under some assumptions in computational complexity. So there are some problems that no matter what this function f is, you cannot solve it in time f of k times some polynomial. There are some problems that you cannot even achieve this kind of running time, n choose k times some polynomial, or more generally, n to the power of f of k for any function f. So one goal is to try to classify which problems are FPT, can be solved in this time or not, and of course, try to find the best f that we can. So I have limited knowledge about temporal graphs, but while talking with Hendrik and while I prepared for this workshop, I saw that this is a very active topic of research, and there is a large number of works on the intersection of the two, and I think that there are many research opportunities here, and various parameters are studied. Solution size, all of the standard structural parameters are studied for problems on temporal graphs. And what's interesting also that there are new parameters to consider here, like the maximum duration. And all the standard topics are studied, like classification, which problems are FPT, solvable in this running time, or W1 hard, which means they are unlikely to. Which problems are in XP, that means that they are solvable in this running time for some function f that depends on k, or para-NP hard, which means that they are unlikely to even have these running times. This is more relaxed than FPT. For example, if we have a problem that is NP hard for some fixed K, say 2, 3, 4, some fixed K, then it is unlikely that you can solve it in this time. Okay? It contradicts, you will get that P is equal to NP. Because then when K is a constant, this is just a polynomial. And also we care about the optimality, kernelization, even there are works on quite recent sub-areas of parameterized complexity in the context of temporal graphs like counting, parameterized counting, and FPT approximation. And let me advertise also where I learned a lot about this is from Hendrik's work. So you can check his thesis and a survey about 3v4 temporal graphs. Okay, so if you want to learn more about the intersection of parameterized complexity and temporal graphs. Okay, so now let me move to the main part of the talk. So let me start with some background. So the problem that we deal with is the disjoint paths problem or disjoint walks problem on temporal graphs. So first, the motivation for this problem comes from the disjoint paths problem or for static graphs. It also has the motivation related to robotics and some applications, which I will not discuss here for lack of time. So let's consider the problem first in the static setting. So this is a very fundamental and famous problem. We are given a graph G, undirected or directed, and we have K-terminal pairs, SITI. These are just vertices in the graph. Okay, these are just pairs of vertices in the graph that we call terminals. This is a multiset, and the objective is to connect them with vertex disjoint paths. Okay, when we need to decide whether we can do this or not. And that means that for every terminal pair SITI, I want to find a path PI that connects SI with TI. And all of these PIs should be vertex disjoint. You can also look at the edge disjoint version, but here we consider vertex disjoint. And the reason that this problem received so much attention in the last few decades is primarily because of the graph minors project. So this was one of the most amazing feats, I think, of modern mathematics. It spent 20 years, roughly, 23 papers, and it proved the conjecture from the 30s, which says that any minor closed family of graphs. So what does it mean? This is just a family of graphs that is closed undertaking minors, that is contraction of edges, deletion of edges, and deletion of vertices. For example, the class of planar graph, the class of forest. If you have a forest and you delete vertex, contract an edge or delete an edge, you still have a forest. So this any minor closed family of graphs can be characterized by a finite set of forbidden minors. So you have a finite set of graphs, and you can say, given a graph, it belongs to your family if and only if it doesn't have this and this and this graphs as a minor. You cannot contract and delete to get one of these graphs in the forbidden set. So why is this so important? So this was actually the inspiration behind the birth of the entire field of parameterized complexity. And in the early days, this is what people thought that parameterized complexity, this is what it's all about. And it yielded numerous concepts and algorithms and structural results for the field and also for other fields. And how it is related to disjoint paths. So disjoint paths is the central components in this project. So a significant part of this project is concerns about structural results and resolution of certain instances of disjoint paths. And what is the situation of this problem in the static setting? This is very hard. So as we will see later for temporal graphs, it is even harder. But even in the static setting, this is very hard. So actually, algorithms that came from graph minors, they even got their own names, galactic algorithms, because they have such bad dependence on the parameter. So I recall that case, the number of terminal pairs that we need to connect. So for general graphs, these are galactic algorithms with this running time and the number of vertices. this is called galactis because this function f is just the tower of exponents. We also know it doesn't have a polykernel, and on directed graphs, the problem is very hard. It's NP hard even for k equal 2. So you just have two terminal pairs that you want to connect. These algorithms are for undirected graphs. Okay, and in the rest of this talk, I will talk about undirected graphs. And because it's very hard, it also received a lot of attention for special graph classes. For example, for planar graphs, split graphs, chordal graphs, and many more. And here, when we will talk about the temporal setting, we will also consider some special graph classes, according to where we can get positive results. Okay, so let's go to what this problem means in the temporal setting. So what is a temporal path for walk? So here we have a sequence of vertex pairs and timestamps. So these vertex pairs should correspond to edges, so that we form a walk. And more formally, when does such a sequence considered to be a temporal walk? So all of these timestamps should be strictly increasing. You can also consider a variant when it is increasing but not strictly. But here let's consider strictly increasing. And what we need is that every pair of vi minus 1 vi that occurs here is an edge at time ti. Okay, so at time t1, v0, v1 is an edge. At time t2, v1, v2 is an edge, and so on. Okay, so you can really walk from, say, v1 and v2 if the edge between them exists in the time t2. Okay, and when no vertex repeats, so all of the vertices that occur here are distinct, so v0, v1, v2, and so on, then the temporal walk is called the temporal path. So what vertices does a temporal walk occupies? So we say that the temporal walk occupies vertex vi at the time interval ti plus 1. Okay, so ti is the time where you leave the vertex vi, and ti plus 1 is the time when you reach the next vertex. So during this entire interval, from where we go from the vertex vi until we reach the next one, we say that we occupy the vertex vi. And of course, there are these corner cases of the first and last vertex. So for example, for the first vertex, v0, the start of the temporal walk, so v0 is occupied exactly at the time t1. Okay, so it's occupied when the path starts at time t1, and then we leave this vertex. Okay, so now what disjoint test means here. So naturally, given this definition, we say that two temporal walks are temporally disjoint if there does not exist the vertex that both of them occupy at the same time. So this is a bit different from disjoint walks or paths because we can have two temporal walks that do share vertices, but they are still disjoint. It is just that these vertices that they share, they need to occupy them at different time intervals. Okay, so you can share vertices, but not at the same time. And then, given this definition, the temporally disjoint path, so walk problem, is defined similarly to the disjoint path problem, just that now the definition of disjointness is different. Okay, so we talk about temporal disjointness. So when we talk about temporally disjoint paths, we want that the terminal pairs are connected by temporal paths. And for the walk version, they need to be connected by temporal walks. Okay. So still about the background, these problems, temporally disjoint paths and walks, were introduced in 2021 in ICALP. And there it was proved that these problems are very hard in the following sense. So for temporally disjoint paths, the problem is NP hard even when k is equal to 2. Compare this to the static setting when the problem is FPT for k. Okay. And so it's NP hard for k equal 2. This is for general graphs. It's even NP hard for paths, but then not for k equal 2, but for general k. And but on the positive side, it is FPT for trees with respect to k. The number of terminal pairs, we can get a running time of the form f of k times poly n. For the temporal disjoint walks version, maybe surprisingly, it is actually easier. So yes, it is W1 hard with respect to k, but it is XP with respect to k. So that in particular means that we don't expect it to be NP hard for any fixed k, while the PEF version is NP hard for k equal 2. Okay, so again, recall that XP means that we can solve this problem in n to the f sum f of k. Okay, so we don't expect it for any constant k to be NP hard, because for constant k, it's just polynomial time. Okay. Good, so now let's move to what is our contribution. So first, we wanted to consider the parameter, the number of vertices in the graph, which is seemingly large. So it seems like it should give us some positive result, FPT, but it turns out that the problem is very hard because temporally disjoint paths and walks, both versions, are W1 hard with respect to n, the number of vertices, even on stars. Okay, but we can still hope to get a positive result because we can consider k as part of the parameter, the number of pairs that we need to connect. And this makes sense because k can be substantially larger than n. And this is indeed what is happening in the reduction where we show hardness. K is substantially larger than n. And why is this? Because recall that the terminal pairs that we have in the input, we get a multi-set, not a set. So the same pair of vertices can appear a very large number of times. So k can be substantially larger than n. Okay? So it makes sense to hope that maybe when we take k as part of the parameter, we get a positive result. Okay, so this is what we did next. We consider the parameter k. So first, recall that this parameter was already considered in the previous work, where it was shown that temporally disjoint paths is FPT with respect to k on trees. On general graph, it's hard even for k equal 2. Okay, but it's FPT with respect to k on trees. So one of our results extends this, and it gives FPT with respect to k plus FES, the minimum number of edges to remove to get a forest. Okay, so for 3, this is 0. So we get the same results, just with k, but this result is more general. Okay, and then what happens when we look at another parameter, which is quite large for most graphs, the vertex cover number, the minimum size of the vertex cover of the graph. But it turns out when you take k with the vertex cover number rather than FES, then it's W1 hard. Okay, so this is for the PEF version. And for the walk version, quite surprisingly, I will say soon why, it's W1 hard, even with respect to k, even on stars, where the vertex cover number is just 1 and FES is 0, because it's in particular a 3. Okay, why is this quite so surprising? It's because this is different than the situation on general graphs. So we recall that it was known that for general graphs, the PEF version is NP hard even for k equal 2, while the walk version is unlikely to be NP hard for any constant k. It is in XP, it's solvable in time n to the f of k. Okay, so for general graph, the walk version is substantially easier, but yet when we restrict ourselves to trees, then the PEF version is FPT with respect to k, while the walk version is W1 hard with respect to k, even on very restricted trees, even just on stars. So here it appears that the walk version is harder, but nevertheless, okay, just let me mention this. This also solved some open questions from the previous paper. But nevertheless, when we talk about paths only, then the walk version is FPT. So we cannot hope to get it on trees because it's hard even for stars. But when we restrict ourselves just to paths, then it is FPT. And I will say a few words about this result now in the more technical part. So now let me give you some technical details for this last result that I mentioned. So we want to prove that temporally disjoint walks is FPT with respect to K, the number of terminal pairs on a path. Okay. So the main idea is to try to reduce this problem to the case of temporally disjoint paths, which we already know is FPT. It's with respect to K. It's even FPT for trees. But what is our problem? What is different when we talk about walks rather than paths? So consider some walk in the solution. Why it is different than the path version? Because this walk can change direction many times. So it needs to reach from some SI, from some source, to some terminal. But it might not go directly, even though the underlying graph is just a path, the solution walk might not go directly from SI to TI. It might not be a path. It might change directions many times. So what do I mean by change direction? So we go from left to right or right to left. Let's say from left to right. So we go in one direction, and now the walk suddenly decides to turn around and go in the other direction. And then it can turn around again and turn around again and do this many, many times until eventually it reaches TI. But notice that if we would have known all of these places where it changes direction, then actually we can segment this walk to just a bunch of paths, right? So if I know that the walks go to this vertex, then changes direction to this vertex, then goes again, then I know I need to find first a path segment from SI to this vertex, then from this vertex, I need to go to this vertex, find another path segment, then another path segment, and so on until the last path segment, which reaches the target TI. Okay, but how can I find these places where the walk changes direction? So what we are going to argue is that the search space, if I want to just even guess these places, this is not too much, okay? The search space is quite restricted. So more formally, we consider the changes of direction of the solution walks. Okay, so what we prove is that there exists a solution where this changes of directions are very specific and very restricted. So there exists a solution such that the number of times that the solution walk changes direction is just order K, the magnitude of the number linear in the number of terminal pairs that we have in the input. Okay, so the number of there exists a solution where this happens. It only changes directions a few times. It's not that every solution does it. We only prove that there exists at least one solution that does it. Okay. So every walk changes directions only a few times. And furthermore, these places where it changes directions, the vertices when we change direction, they're in distance order K from all the sources and sinks, from all of the SI and TI. So every place where we change direction is at a distance at most K from some SI or TI. Okay. So what it means, we look at the underlying path. There are some places where the SI and TIs occur. Every place where you are going to change direction is just very close to each one of them. And then you are going to change direction only a few times. Okay, so overall, I will soon say a few words on how we prove this. But overall, this gives rise to guessing where all of the changes of direction occur. So by guessing, I just mean that we do exhaustive search. So we try all the possibilities of where the changes of directions will occur and try to solve each one of the resulting problems. If at least once we get yes, then great, we got a solution. And if for all of the guesses we failed, then no, there is no solution. Okay, because we are guaranteed that at least one guess will be correct, will comply with some solution. Okay, so how do we do these guesses? So for every walk, we guess some order K places where it is supposed to change the direction and exactly what is their order. Okay, so where can it change direction? It must be at vertices out of some set of size order K square, right? Where can we change direction? at the distance order k from every Si and Ti. We have only 2k Si's and Ti's, at most 2k distinct Si and Ti's. So the number of vertices close to them, where we can change direction, is just order k squared. And then for a walk, I need to guess at most order k vertices. I need to guess at most k times, order k times vertices from this subset of size order k squared. So this is just some function of k many guesses. And I do this for every walk. There are just k of them, so it's just to the power of k. Okay, so there are only some function of k many guesses, and I know that if there is a solution, then there is one that complies with one of my guesses. Okay, so it really changes direction where I guessed it should be. And then what it means, so let's look at some guess, and we reduce the problem to the path case, to temporally disjoint paths. So I have some walk, I guessed exactly where it is going to change direction, and now I just segment it. So instead of trying to connect Si and Ti by a walk, instead I try to connect Si with the first change of direction by a path, then from the first change of direction to the second by a path, from the second to the third by a path, and so on until I have the last path segment that reaches Ti. So every walk is replaced by a collection of paths, but still some function of k, so that's okay. The parameter is still the function of k. We need to be a bit careful here, because the collection of paths that we get here, there is some precedence constraint. So I need that getting from Si to some, the first change of direction will happen before I go from the first change of direction to the second. That will happen before I go from the second to the third, and so on. But no known algorithm can handle that. It can be modified so that it handles this as well.
Sorry, Meirav?
Yes.
We're running short on time.
Yeah, I just have like 2 minutes.
Just a little bit more. That's okay.
Yeah, so 2 minutes is fine.
Yeah, should be fine.
Yeah, so I just have 2 minutes in the talk to finish. So
Perfect.
how do we show that there are only a few direction changes and they occur only on this very specific place?
Hello, Meirav, can you still hear us? We cannot hear you anymore. We're going to check if there's a technical problem.
I think we can hear you. It's probably Meirav that we've lost.
Oh, okay. Yeah, we can wait a little bit until she reconnects. Maybe because I told her that she only has a bit more time left, she got mad and quit the conference.
For some reason, the Zoom dropped.
Yes, we can see you and hear you now again.
Yeah,
you can just start again where you left us.
Yeah, so I just have like 1 minute left. So I want to say, why does the walk change its direction? Why doesn't it just stay in the same vertex but it does this? So the reason look at that the walk changes direction, look for example at the red walk, because it needs to clear the path for another walk that needs to start or end. So here we have some terminal where a different walk, the blue one, starts or ends, and this propagates. So now there is another path or walk rather, another walk, the green one, that also needs to clear the path for the red one. So, and this propagates to the purple and so on. But we only have k walks, so it can only propagate k steps. So all of the places where we change direction are just at a distance at most k from some terminal. And furthermore, notice that when do we change direction? Because some walk, here the blue one started or ended, and that only happens k times. Okay, so this is the main insight behind the proof of the few changes of direction where they occur. And of course, this requires a proof, but I just wanted to give the insight. So finally, let me conclude with some open question. So you can also consider the problem with respect to other structural parameters. In particular, it will be interesting to consider parameters unrelated to vertex cover in SVS. For example, cut width. Then you can ask if temporally disjoint paths or walks is FPT for K plus cut width. And also, all of our hardness results hold when the solution paths or walks are short. They just use few edges, but their duration is long. So the time that passes from the time that they start in SI until they end at TI, that is very long. So it might be possible to get positive result for the parameter K plus maximum duration. Okay, so that's all. Thank you for listening.
We have time for 1 or 2 questions. So I had a question since a few minutes ago, but I think you partially answered that. At first, I was thinking why walks would go back from where they came from. Why couldn't they just wait? And so you said that this is to make room for another path to come in, or another walk to come in. And
yes.
So is this? So I thought maybe they backed up so they would be able to go to a place in the path where they would be able to switch places with an incoming walk. But I suppose your model doesn't allow any crossing even on an edge, right?
No.
Okay.
No,
So what
so
if you do allow crossing on an edge? Does that change much?
Yeah, then it's different.
Okay.
Yeah, if you allow them to cross on an edge, then it's different.
Okay.
But it's interesting. This can be studied in future works.
Yeah. Very well. Let's clap again.
Okay, thank you.